Okay, so now we come to covalent compound naming. It becomes really important that you identify or you know the rules associated with naming covalent compounds and you be able to apply them into situations that you haven't quite seen before. And the first thing is you need to be able to identify the first element in the compound. And what you do is you move from left to right across the periodic table. The only difference with that left to right across the periodic table is that actually hydrogen fits in between nitrogen and oxygen. And that's kind of a weird, archaic rule. There is a reason for it. If we look at the periodic table, um, as far as nitrogen and carbon, that tends to be where it would fit if you're looking at it in terms of bonding order and those sorts of things. So that's why we tend to put it there. But you do need to know that that is where it goes. So the first element is the one that's furthest left, with the exception of hydrogen. And then the next thing you need to do is you need to be able to determine a prefix if necessary. Now, if there's a prefix, we do not put mono with the first element. If there is only one atom there, for example, if I have this right here, the first element is carbon, okay? I would call it carbon, not monocarbon, okay? So there is no prefix if there's only one thing for the first element. Now, if there's two, if you have something like C2O4, you could say yes, C2O4, that means, well, that's not a great example, but if it's C2O4, you could say it's dicarbon, okay? But in this case, that's not what we have. So we've determined if a prefix is necessary. The next thing is we identify the second element. The second element in our case is oxygen. We need to determine if there is a prefix necessary. There is always going to be a prefix associated with the second element. So, since I have one oxygen, it would be mono, because there's one. You have mono, di, tri, tetra, petra, hexa, hepta, octa, nona, and deca. You do need to know these. Okay, you can't. I mean, you have to memorize them at this point. It goes in order. You should be able to do that relatively easily. Then you write the name of the element, monox, and then what it tells you to do is you replace the ending of the second element with "ide." And this takes a little bit of practice more than anything. So this is actually carbon monoxide. You replace the "igen" with "ide." And it takes practice more so than anything. There's no hard and fast rules. The easiest one are the halogens because it's chloride, fluoride, bromide, but it gets a little bit trickier when you're talking about other things. So as we work with them, you'll start to see kind of where you place the "ide." So here's an example. It says the molecule CH4 forms a tetrahedral shape as shown. We'll talk a little bit more about shapes later. It says determine whether the molecule as a whole is polar or nonpolar using the periodic table of electronegativities. So what we want to do is the first thing we want to do is we want to look at an individual carbon hydrogen bond. In order to determine whether that bond is polar or nonpolar, we consult our periodic table. We say, okay, hydrogen is 2.2. We say carbon is 2.55. And we say there's a difference of 0.35. In other words, the electrons are drawn towards the carbon. Well, in that case, you would think that this would be a polar bond in which you have a partial positive and you have a partial negative. Okay? But that's an individual bond. If you look at the shapes, though, you have this is pulling this way, this is pulling this way, this is pulling this way, and then that's pulling down. As a result of that, the net pull ends up being zero because of something called symmetry. It's a little bit hard to tell when it's in this tetrahedral shape, but if I draw it another way, it should be fairly evident. If you have it look like this, you can see that whenever I pull this way, I have a hydrogen to cancel me out. Whenever I pull this way, I have a hydrogen to cancel me out. As a result, the molecule as a whole is what we call nonpolar. Okay, since it's nonpolar as a whole, even though each individual bond is polar. So you need to be able to recognize situations in which you have polar bonds that turn into nonpolar whenever you put them together. And the key to that is symmetry, if you have something to cancel something out. It says name the following covalent compounds. So a lot of you go, oh, water, that's easy. Yes, that is technically the name for that, but there is a better name according to the formulas, and it is dihydrogen because I have two hydrogens, and then it is monoxide. So you have dihydrogen monoxide. Okay, you also have this right here, which we've already talked about, is carbon monoxide. Because remember, you don't want, excuse me, monoxide, because you don't associate mono with the first element. Okay, it's only with the second element that you would put a mono. Next, it says write the chemical formula for these. So it says dinitrogen. So what I would do is I put nitrogen, and since it's di, there's two of them. And then pent means five, and then oxide is oxygen. So dinitrogen pentoxide is N2O5. The next one is carbon tetrachloride. Okay, the first element is carbon. There's only one of them, and the reason why there's only one of them is there is no prefix. And then tetra means four, so I have four chlorines. So you have carbon tetrachloride and dinitrogen pentoxide.